Have you ever stood at the shores of a beach and, as you shifted weight from one foot to the other, slowly but surely began to sink? The more you shuffled in place, the more sand would give way, as if it's melting right under you? If so, you've experienced a phenomenon known as liquefaction. Liquefaction may be defined as wet soil exhibiting behavior of a liquid when a stress, such as vibration, is applied. The soil, losing its ability to hold a solid structure, deforms and collapses with the continuous stress. Just as with any liquid, such as water, behavior of neighboring materials of varying densities will act in accordance. Dense objects resting on the folding material will sink into the soil, while more buoyant objects buried will rise to the surface and be unearthed. Liquefaction is an occurrence more common than you think. If you live anywhere with a consistent accumulation of water, such as wetlands, lakesides, reclaimed land, and beach shores, you've probably experienced it at least once. Coastlines in island countries are extremely susceptible to liquefaction due to their location in reference to water and the probability of earthquakes that would induce the occurrence of the phenomenon. Despite how common it's been made to sound, liquefaction requires a rather specific set of conditions to occur. First, the soil must be saturated and relatively unconsolidated in order for it to be susceptible to liquefaction. Smooth, rounded, and fine-grained soil is preferred, such as sand, in order for particles to slip. By itself, these conditions will not liquefy without a catalyst. An outside force is required to initiate soil failure, which is the application of a stress. Cyclic loading is the most common applied stress of liquefaction. Repetitive motion, such as vibration, or a sudden violent shift in stress conditions, will complete the process. The science behind liquefaction is a curious balance between the pore pressure and effective applied stress. The total stress is a sum of both, as seen in the following equation. What's notable in this equation is that the effective stress is the force keeping particles stiffly in contact, while pore pressure is the pressure exerted by water trapped in the pockets in the soil. As the saturated soil experiences the applied stress, fine-grained soil particles have reduced grain-to-grain contact and continually slip. This slippage is a reduction in effective stress. As water is incompressible and experiences a reduction in volume, pore pressure increases and the water in the pores forces the grains apart. By this time, total stress is equivalent to the pore pressure, as effective stress is essentially zero, meaning there is virtually no grain-to-grain contact between particles in the soil. This allows the soil to flow as a liquid despite being comprised of solid soil particles. Eventually, soil particles will compact and water will be forced to the surface. The following demonstration exhibits the traits of liquefaction: soil failure, fluid motion, and water rising to the surface. With the addition of vibration to a saturated soil, weights placed on the surface initially begin to sink at an angle before the shapes begin their downward descent. Water bubbles to the surface as the grains compact. From a side view, soil failure is more evident. Notice how the weight initially sinks at an angle before continuing at a steady descent. The motion of the water, forced from the pores of compacting sand, can be tracked with the darker particles surfacing along the liquid. Well, why is it important to know about liquefaction? For starters, the dangers of quicksand is as well known an example of liquefaction to anyone. Applied to a citywide scale, liquefaction is an important natural phenomenon that wreaks great havoc on buildings constructed on the weakened, saturated soil. Shock waves through the earth, such as severe earthquakes to even mild tremors, can easily begin the sinking process, and in the Midwest often cause damage to transportation arteries and cantilevered beams. In other experiences, the unstable ground of liquefaction soil can also unearth pipelines and damage internal systems reliant on a steady soil body. Despite its seemingly innocuous nature, liquefaction is something important to account for all aspects of life, ranging from transportation, city planning, agriculture, and various other tasks that require consideration of the proposed soil site.